At 1600 hours local time on December 9, 1942, a heavy bomber reached an irreversible operational threshold. The home airfield at Adak was completely obscured by whiteout conditions. The aircraft was a consolidated B-24 Liberator, often described in later records as a B-24D. Serial number 4-0-2367. It operated under the United States Army Air Forces under the 11th Air Force and flew within the Aleutians command structure centered on the 28th Composite Group, with the aircraft commonly associated in accounts with the 21st Bombardment Squadron. Returning under orders, the crew had flown a weather reconnaissance run over Kiska and Attu. In the Aleutians, that single task determined whether larger bomber forces could launch at all, because commanders lacked satellite air visibility and depended on forward atmospheric reports. The mission demanded crews push into marginal conditions and absorb maximum weather exposure to bring that data home. On the return, Adak vanished into subarctic whiteout, blowing snow and maritime fog collapsing visibility to zero. Period radio navigation could not place a heavy bomber precisely onto a blind runway threshold, turning the weather into a hard operational limit. Fuel became the only calculation that mattered. The tanks could not support circling while the storm moved, and at 1600 hours the gauges showed the point of no return. Attempt a missed approach in zero visibility, and the aircraft would burn the exact fuel needed to reach any alternate geography. Diversion away from Adak was therefore mandatory. The flight path shifted away from the storm center, directing the bomber down the Aleutian chain toward Atka Island near Bechavan Bay. The diversion terrain on Atka Island defines the modern site perimeter. It is a remote subarctic marsh and tundra flat with weak ground bearing and narrow weather windows, limiting investigators to brief, carefully timed access. Those physical limits are then tightened further by the administrative protections that govern the wreck. In 1979, the federal government placed the site on the National Register of Historic Places, converting it from a recovery target into an archaeological baseline. From that point forward, surveys treated the airframe as a fixed reference and measured change against an undisturbed wreck field. The bomber remains where the forced landing ended, with its context preserved as evidence. Non-intervention rules now frame every modern visit. The site is treated as a bounded evidence field, and crews cannot reshape terrain, clear mud, or stage intrusive access. Reaching the valley demands heavy logistics for only a short visual window, and the marsh has permanently seated the lower fuselage in place. Exposed to wind, snow, and salt weathering, the surviving structure functions as a standing reference for forensic and historical structural reading. A B-24 at roughly 36,000 pounds empty carries unforgiving kinetic energy in any off-runway descent. The crew had to choose between ditching into freezing North Pacific swells, where breakup, sinking, and lethal exposure were likely, or committing to unknown ground. The pilot rejected the water and put the aircraft down gear up into a marshy Atka Island lowland. The decision to keep the landing gear retracted was a mandatory operational constraint dictated by the terrain. If the heavy tricycle landing gear extended into the soft tundra, the narrow wheel profile would immediately sink and lock into the soil. This sudden resistance far below the center of gravity would shear the nose strut, violently pitching the aircraft forward and guaranteeing a catastrophic tumbling breakup. By retracting the gear entirely, the pilot forced the wide underbelly of the fuselage to act as a broad friction surface against the mud. The specific soft mud composition of the subarctic marsh provided immediate energy attenuation via terrain. As the flat underbelly plowed through the saturated ground, the extensive drag force bled off the kinetic energy rapidly, preventing a violent ground loop or a spark-induced fuel fire. Despite this highly controlled energy dissipation, the heavy airframe could not withstand the uneven deceleration forces generated by the tundra surface. The bomber features a long, tubular aft section that concentrates extreme stress during a flat belly slide. As the rigid forward section, heavily weighted by the wing center box, decelerated rapidly in the deep mud, the residual momentum of the lighter tail section continued pushing forward along the crash vector. This opposing kinetic force created severe structural bending loads across the midsection of the fuselage. Under this immense mechanical leverage, the airframe failed structurally and broke completely apart just aft of the wings. The visual preservation of this exact failure point provides modern surveyors with direct positive verification of the standard aft separation pattern associated with this specific aircraft design. No post-crash fire meant the structural evidence stayed readable, with major sections settling into the soil where they failed. Over time, federal protection formalized that preservation. In 2008, the site was incorporated into the World War II Valor in the Pacific National Monument, bringing it under a monument management framework rooted in the Antiquities Act of 1906. The practical effect is strict control. Disturbance or removal requires explicit authorization, and preservation in place is the default. That mandate bars extraction, cutting, lifting, or any ground-disturbing work. Survey teams cannot introduce heavy rigging or use tools that would clear, pump, or excavate the mud, and even small hardware removal is prohibited because it alters context. The wreck is managed as a no-touch evidence field, so how do investigators extract technical data without crossing the non-disturbance boundary? In 1978, formal condition surveys ran into an absolute sensor limit. Much of the lower structure was unreachable, and some armament and high-value components had already been removed over the years. When civilian historians arrived, they accepted an in situ, non-invasive approach: photography, measured observation, and external visual recording, documenting only what the wreck exposed above the mudline. The team worked under non-disturbance conservation, keeping the bomber exactly where it lay to preserve spatial context. Unlike standard aviation forensics, where investigators cut structure or treat corroded metal in laboratories, survey-only practice here prioritizes the relationship between soil, water table, and airframe. If a component is buried or a view is blocked, it stays that way, and the map is built around what the site allows. To capture maximum data without touch, the surveys shifted to in situ baseline mapping, a dimensional grid built from overlapping imagery, where rivet lines, torn edges, and oxidized panels become fixed reference points. Historians conducted the main condition survey in 1978 and returned in 1983 to verify change, using photogrammetry from predetermined distances and angles to create intersecting visual fields. All measurements stayed above the mudline as teams walked the perimeter and recorded the condition of nacelles, wing skins, and separated fuselage sections under a zero-impact handling standard. The historical removal of the armament decades earlier required the survey teams to carefully document empty gun mounts and open structural voids. These exposed internal cavities provided the only limited line of sight into the internal frame condition. By systematically recording these specific access points, the surveyors maximized their visual reach without breaching the outer skin of the aircraft. The resulting photographic record achieved the key administrative objective: a defensible baseline that could be archived and reused without permits for sampling or excavation. It demonstrated that a high-fidelity condition assessment was possible even when researchers were barred from touching the airframe. With that baseline established, what specific structural cues remain visible on the forward fuselage to verify the bomber's exact production block? Above the mudline, the upright forward fuselage preserves manufacturing details that can be read without contact. The intact flight deck and bombardier compartment allow investigators to place the airframe into a narrow early war window and support a 1941 build timeframe from external geometry alone. The primary anchor proof for this specific aircraft rests at the extreme forward point of the fuselage. Many later liberators carried a prominent top astrodome intended to assist navigation, but this coherent forward structure does not show that feature. The upper nose instead presents a smoother contour, and the port side of the nose includes a small observation window often associated with early production examples. Taken together, these visible cues strongly support an early configuration within the Liberator production run. Even under strict non-contact constraints, archival production records can be consulted, but the decisive evidence here is the forward aluminum itself, its openings, fittings, and contours, captured through baseline mapping without breaching the hull. Strict federal heritage controls prohibit excavation, leaving the underbelly, bomb bay doors, lower bulkheads, and wing root connections buried under saturated soil. Surveyors can confirm identity and early configuration from the intact forward section, but they cannot inspect buried longerons or quantify corrosion below the waterline, creating a hard-proof ceiling on lower hull integrity. With the lower structure sealed by law and terrain, the separated wreckage aft of the wings becomes the next readable source of mechanical truth. What does it reveal about the airframe's limits? At this protected site, the wreck's spatial geometry becomes the primary interpretive tool. Instead of extracting and reconstructing frames in a hangar, investigators read detached assemblies in place, using the distance, angle, and resting orientation of the severed tail relative to the main fuselage to infer load paths and impact sequencing. The unedited ground scatter substitutes for physical reconstruction because moving debris would erase the context that carries the timeline. The physical distribution of the empennage provides specific forensic markers that define the final moments of kinetic movement. Beyond the primary fuselage break, the twin vertical tail fins separated entirely from the main empennage structure. Survey teams mapped these isolated vertical stabilizers exactly where they fell in the marsh. The resting angle of these fins, combined with their measured distance from the severed tail section, visually confirms the aft failure sequence. The spread geometry proves that the empennage experienced extreme lateral whipping forces as the main body decelerated rapidly in the deep mud, snapping the vertical fins from their mounting points. Investigators successfully locked this structural failure mode into the official record strictly by mapping the spread geometry of the detached evidence. Moving even a single piece of torn aluminum from its original resting place would destroy the spatial context that proves this mechanical timeline. This rigid physical evidence contrasts sharply with fragmented documentation about the people on board. Published sources do not agree on the exact number aboard at the time of the forced landing. The National Park Service account emphasizes that the occupants survived and notes a fractured collarbone suffered by Captain Lind, while at least one independent accident database lists a smaller number of people aboard and reports additional injuries. In this case, the wreckage can speak clearly about how the metal failed, but the paper trail remains inconsistent on the manifest and the distribution of personnel during the breakup. While the surface-level debris field answers the mechanical sequence of the breakup, investigators face a hard-proof ceiling regarding long-term material survival. The visual mapping of the detached tail section is strictly limited to the exposed upper aluminum skin. The subsurface corrosion rates of the submerged aft components remain completely untested. Saturated subarctic soil can create complex corrosion conditions, especially where dissimilar metals meet and where moisture cycles through the structure. But without sampling, the true corrosion rate below the mudline remains difficult to quantify. Because strict heritage controls govern the site, investigators cannot trench around the severed tail or extract lower frame samples for controlled metallurgical testing. The soil chemistry surrounding the buried structure is effectively unmapped, leaving engineers without the data necessary to confidently project long-term failure timelines. That restriction leaves subsurface material condition largely inferential, but it does not negate the survey's core achievement. The map geometry of the detached tail preserved the failure sequence without disturbing evidence. With the maximum allowable data captured above the mudline, how is this deteriorating subarctic site managed for the long term? Across the decades that followed federal recognition, the wreck's status shifted from a remote artifact to an actively protected heritage resource, steering policy toward preservation in place rather than salvage. Monument designation drew a defined legal enclosure around the marsh and wreckage, with the Antiquities Act of 1906 governing the footprint and prioritizing spatial integrity over physical recovery. Management is preservation in situ with tightly controlled access. The airframe is not a recovery project and it will not be extracted for display. Routine stabilization, shelters, shoring, drainage changes, or chemical inhibitors is constrained because it would alter site context and require specific authorization. The policy therefore accepts continued weather-driven degradation, including freeze-thaw stress, as the trade-off for keeping the wreck and its spatial evidence intact. Future monitoring operations are restricted entirely to periodic visual observation. When permitted access, official inspection teams can only conduct passive visual assessments from the designated perimeter. They must compare the present structural geometry against the established historical photographic records to calculate the precise rate of environmental collapse over time. They track the oxidation of the exposed aluminum alloys, the gradual settling of the heavy central structures deeper into the mudline, and the progressive mechanical failure of the remaining visible rivet lines. The site functions strictly as an observational laboratory for long-term material survival in an extreme subarctic environment, generating data solely through passive exterior measurement. The primary achievement here is the baseline itself, early mapping. Locked key manufacturing and damaged geometry into the archive before settling and weathering could distort it. With legal protections preventing alteration, the site now functions as a long-term observational reference for early wartime aircraft structure under extreme subarctic exposure.